Geometry, Section 10.2, Arcs and Chords. By the end of this lesson, you should be able to use the properties of arcs and chords of circles. As with the last section, we do have a lot of vocabulary that we need to make sure we understand so that we can use the theorems appropriately. So some of the vocabulary we have deal with angles and arcs. The first one is a central angle. And a central angle is an angle whose vertex is in the center of a circle. So I'm going to draw in angle AGB, and angle AGB is a central angle because its vertex G is the center of the circle. A minor arc is part of a circle that measures less than 180 degrees. And minor arcs will always have some sort of central angle that it corresponds with. And so let's talk about arc AB. You will write that as two letters, it's two endpoints on the circle, and you're going to have a little arc symbol above it. And this is related to the measure of angle AGB, but we'll get into that a little bit later. A major arc is going to be an arc that measures more than 180 degrees of the circle. And for every minor arc, there is a major arc that is related to it. Major arcs, you're going to name with three letters. So this major arc is going to still have the endpoints A and B, but so that I know that it's a major arc and not a minor arc, I'm going to include this point C that it passes through. So we'll name this one ACB and have the arc symbol above it. And last but not least, we have a semicircle. So we talked about arcs that are less than 180 degrees, arcs that are more than 180 degrees, and a semicircle is part of a circle that measures exactly 180 degrees. So if we're talking about a semicircle, it will end up being exactly half of the circle. Semicircles also need to be named with 3 points. So I'm going to add in a point H here and a point L. My semicircle will be named HCL. The measure of a minor arc, like we were talking before, has relationships with the central angle. So looking at this, we have the measure of a minor arc is defined by its central angle. If I wanted to find out the measure of arc AB, that is going to be related to its central angle. And the relationship is that they're exactly the same. So the measure of angle AGB is going to be equal to the measure of arc AB. If we're to say that this is 62 degrees, then that means the measure of arc AB is 62 degrees. The major arc is going to be related to this central angle as well. We know that there are 360 degrees in the circle. So the major arc is going to be 360 minus whatever this is. So for us, we'll go ahead and say that the measurement of arc ACB is going to be equal to 360 minus 62. So we can say that the measure of arc ACB will be 298 degrees. Just like segments, two arcs are congruent if they have the same measure. And also like segments, we had a segment addition postulate, an angle addition postulate, and so now we have an arc addition postulate. And similarly, it says that the measure of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. So if I wanted to find out what the measure of ABC was, then I can take a look at the two arcs that make it. And that would be arc AB, this arc here, as well as arc CB. And arc ABC will be whatever these two arcs added together. Just for some practice, let's take a look here. And it's asking us to find the measure of these following arcs. The first one is arc DG. I know since it has two letters, it's going to be the minor arc, DG. And to find that, that'll be equal to 70 plus 80, because our arc addition postulate said that I can add these two together to come up with the total arc measure. So arc DG will be 150 degrees. Next we have arc DGH. Since it has 3 letters, this is a major arc. So I'm going to need to find out what this entire arc here is. I have all of the corresponding central angles, so I can take these measures and add them up to come up with the sum or the total measure for arc DGH. So here I'm going to add up 80 plus 70 plus 120, and together that's going to make up my major arc's measure. And this will end up being 270 degrees. Last we have arc DH. And I don't have a central angle that corresponds to it, but what I do know is that the entire circle is 360 degrees. And I know that arc DGH is the complement to arc DH, so if I have 360 minus 270, I should be able to come up with the measure for this arc, which will be 90 degrees. We do have a few theorems, 4 in total, that we're going to talk about today. And the first one is that if a diameter of a circle is perpendicular to a chord, then the diameter bisects its chord and its arc. So here we see this diameter. I know it's the diameter because it's passing through the center of the circle. And this is saying that it's going to, if it's perpendicular to it, it's going to bisect the chord and the corresponding arc. So I can say that DE is congruent to EF, but what I can also say is arc DG will be congruent to arc GF. Our second of our 4 theorems is going to be the converse of this. So we can make note of this in our notes that these are converses. And this says that if a chord is perpendicular bisector of another chord, then the first chord is the diameter. So if I notice that it's perpendicular and it bisects it, then we can say that JK is the diameter of the circle. Our last 2 theorems for this section are the following. If we have a circle, or in congruent circles, if we have 2 minor arcs that are congruent, this is only going to happen if their corresponding chords are congruent. So if I wanted to say that AB and BC were congruent, I would only be able to say this if I know that these chords that cut them off are also congruent. So AB is congruent to BC only if the segment AB is congruent to the segment BC. And finally we have, if in the same circle or congruent circles, 2 chords are congruent only if they're equidistant from the center. So I can say here that these chords AB and CD can be congruent only if these distances are the same. So we'd have to see that EF is congruent to EG. And remember that the way we measure the distance from a point to a line is that they have to be perpendicular to one another. Here's a couple practice problems. And for this first one, we need to find the measure of arc RS. Well, if we go back to one of our previous theorems, it says that if we have a diameter that's perpendicular to another chord, it's going to bisect that chord and its corresponding arcs. So because of that, we can set these 2 measures equal to each other to solve for x, which will help us to solve for the measure of arc RS. So 3x plus 24 will be equal to 7x. In solving, I'm going to have that 24 is equal to 4x, and x will be equal to 6. Because x is equal to 6, I can substitute that in and find out that the measure of arc RS is equal to 7 times 6, which would be 42 degrees. Our next example tells us to find HK. And we know that DG is equal to JL, which is 24. So these segments are each 24. And we also know that DH is 13. Now this is a combination of several of our theorems. What we're able to say is that since we have this part of a segment perpendicular to this chord, and I notice that it comes from the center of the circle, it means that it was originally, or it could be considered part of a diameter, which means then is this is congruent to this. This chord is bisected. And if the total is 24, then that means this portion here is going to be 12. And we're asked to solve for HK. I also know that these segments have to be congruent to one another because of another one of our theorems that said that if two chords are congruent, then they're equidistant from the center of the circle. So if I can figure out what FH is, then I know what HK is. And I can figure out what FH is by the Pythagorean theorem. So I'll set that up and say 13 squared is equal to 12 squared plus, I'm just going to call it FH squared. In solving this, we end up with 25 is equal to FH squared, so it means that FH is equal to 5. Since FH is equal to HK, we can go ahead and say HK's measure is also 5. This one's one of the more complicated problems you'll solve because it involves multiple theorems, but it is good that we understand it. And that is it. It's another long video, but there's a lot of notes to take from this section. But we're finished and it's time for our joke. And our joke is one from our very own geometry student. And it says, how do you make a tissue dance? Well, you put a little boogie in it.